Well, good morning. Happy Friday to you. I hope you guys are going along pretty well. From the communications that I've had with you and the questions that you've had, as I've always said, you guys ask the best questions. I've been enjoying being able to teach some pretty complex stuff to you, and you seem to be getting it. Anything that you don't get, keep on calling, keep on texting. We'll keep on answering. Let's pray, and I want to do a little bit of review of where we're at. Father, we thank you for all of the technology that you have given us, that you allow us, Lord, to be able to communicate even though we don't see that we don't see each other. And Father, I do look forward to the time when I can see Philip and Sarah and Lucas, and we can communicate a little bit closer once again. But Lord, for right now, I thank you for this material. I thank you for your leadership. I thank you, Father, that you've given us all of these topics to study and to just increase not only increase our knowledge, but increase our thinking ability. That we not only know information, but we know how to think logically more and more. And Lord, I pray for you to give us that guidance again in today's class. In Jesus' name, amen. A little bit of review because I've attacked you guys with a barrage of information. We've talked a lot. We've talked about a lot of ring theory, and we've talked about. We haven't talked a lot about topology as far as it has to do with the ring theory yet. We're going to do that today. But just to review a little bit about the ring theory that we've been talking about, recall that a domain is a commutative ring that has the property that no two non-zero elements can multiply together to give you zero. Now, a domain is a prime commutative ring, but a prime ring in general, commutativity or not, has the property that if I multiply two non-zero ideals together, then I can't possibly get the zero ideal. And of course, in the commutative case, that reduces to what I just said a few moments ago. The theory of prime rings has become hugely important. You know, back when you and I first met and we started talking about the art of mathematics, we talked about how you can pursue the four main fields of mathematics, namely analysis and topology and geometry and algebra. You keep pursuing and you keep pursuing and keep pursuing. And then when you get to the other side, all of these things really start to merge. You're there. You're seeing that merging. You're seeing the artwork of God as he has put together these fields. And it's been amazing to me that men have pushed each one of these fields farther and farther, and sometimes almost by accident stumble into the other field. Who would have thought that studying ring theory and prime rings and the like, who would have thought that that would have led to topological things? Who would have thought that studying polynomials and the solutions to polynomials, the zeros of those polynomials, who would have thought that that would lead to topology as well? Who would have thought that it would lead to the study of prime ideals and prime rings in algebra? It's just it's an amazing phenomenon as to where man has gone mathematically to lead him into everybody else's field. And so we're touching on that today. Today we're going to touch on all three: geometry and algebra and topology. Now, the geometry of it has to do with what are called varieties. And an algebraic variety is a set of zeros to some set of polynomials. And we talked about affine spaces. An affine space is really a translation of one of the Euclidean spaces. So if I take the Euclidean plane and I translate it by some non-zero vector, well, then it's no longer a vector space because zero doesn't live there anymore. But I still have something that topologically resembles that Euclidean space. Namely, it's homeomorphic to R2. So, and of course, you can do that for any dimension. It's a little easier to visualize it if it's a plane, but if you want to move R17, translate it someplace else, you still get a homeomorphic copy of R17. Prime ideals have an interesting theory behind them that connects algebraic geometry with topology. And part of that theory has to do with how many prime ideals you can stack one on top of another. Now, we talked about what's called the Kroll dimension of a ring. The Kroll dimension of a ring is how many prime ideals you can stack on top of a given one. So this given one is, say, the 0th one, and if you can embed that in another prime ring, then you have a stack of length 1, a chain of length 1. If you can put that in another prime ring, then you have a chain of length 2. And a perfect example of that is in the polynomial rings. Now, in the polynomial rings, if you have the polynomials in n variables, then you can stack those prime ideals n deep. And that's as deep as you can do it if you have an algebraically closed field, like the complex numbers, and you start and you have the n indeterminates, x1 through xn, so the polynomial ring in indeterminates, then the dimension of that polynomial ring is the number of indeterminates. It's n. And the beauty of that is that when you draw that back to algebraic geometry, you have dimension in another sense. And it turns out that the two dimensions are equal. The topological dimension over here is equal to the Kroll dimension over here. I mean, these things mesh beautifully. You know that if you have, well, you know what? Let's prove some results. We talked about the radical of an ideal. The radical of an ideal is the collection of all of the elements such that some power of that element is contained in that ideal. Well, of course, the first power of every element in an ideal is in the ideal by its definition. And so the radical of an ideal certainly contains the ideal itself. It's a bigger ideal in general. Now, we're going to be dealing with today commutative rings with 1. Nice things happen in commutative rings with 1. Let's suppose that I have any commutative ring with 1. Then for every ideal in that commutative ring, I can embed that ideal in a maximal ideal so that a maximal ideal that contains that given ideal. So now commutative rings with 1 can have a number of maximal ideals. Think about the integers. How many maximal ideals are there in the set of integers? And the answer is infinitely many. all of the multiples of the primes are maximal ideals in the set of integers. The only prime ideal of z that is not a maximal ideal is the zero ideal. It is a prime ideal because you can't take any two non-zero elements, multiply them together, and get zero. So it's prime, meaning that z is a domain. But it's not zero is not a maximal ideal, because if it were, then there wouldn't be any other ideals other than all of z. If zero were a maximal ideal, z would be a field, and of course it's not. All of these concepts we're going to try to tie together as much as is possible, and so let me start. Let me stop talking and start talking. One of the examples that I gave you before, I didn't want to be misleading about, but let's see if how that falls out. Okay, it was the example in the complex numbers with two indeterminates. And the question is, what are the prime ideals in this ring? As it turns out, it's easy to know the prime ideals in the ring with two indeterminates. It's even easier to know them in a ring with one indeterminate, c of x. But when you get to three or more indeterminates, it starts to get really pretty complicated. And so there are some nice open questions in that regard. But the prime ideals in this ring, there are three types. First of all, 0 is prime because, and I'm going to call this ring R, because R is a domain. It doesn't have any zero divisors other than 0, and so I can't multiply two polynomials together and get 0 unless one or the other is 0. The second type of ideal that is a prime ideal is an ideal that's generated by x minus, some a sub alpha, y minus some b sub alpha, because over C, these are the only irreducible polynomials. So these are the maximal ideals in R. And then finally, ideals generated by an irreducible polynomial. Now, you might be saying, now wait a minute, C is algebraically closed. So there are no irreducible polynomials over C except the linear ones. That's not true. In C of x, one indeterminate, that is true. There are no irreducible polynomials in one variable over C because C is algebraically closed. Every polynomial has got all of its roots in C. In fact, we just finished proving that in abstract math, believe it or not. No, we didn't. We just finished proving that in complex variables. I forget. You can prove it everywhere. It's still true. All right. But there are irreducible polynomials in C of xy. I gave you a couple of examples before. But notice that P of xy equal to, say, x squared minus y is irreducible in R, in C of xy. You can't factor this, because factoring it would mean lowering the dimension of the factors, and I can't write this. This is dimension 2, so there's not too much lower than you can get except for 1. I cannot write this polynomial as a product of two linear polynomials. So there are many, many, many irreducible polynomials for R. Okay? You know, when you do your notes for a class, make sure they're all the same size, because when they're not, this thing goes weird. Okay. Now let's recall this. What do I mean by the ideal generated by a polynomial? I mean all the multiples of that polynomial if I'm in a ring with, in a commutative ring with 1. Now remember, if you were in a non-commutative ring, we had to take multiples on the left and multiples on the right and multiples for both sides, and they had to take the polynomial itself. But if you have a commutative ring with 1, it's just the multiples of the polynomial, because all of those things are already automatically included. So let's see. I'm going to make our definition. Let's do some topology. Definition. Let R be a ring and I'm going to say our primary interest is going to be when R is commutative with 1. But it's not necessary for this definition. Okay, let R be any ring at all. Then the spectrum of R, denoted by SPEC of R, is the set of all the prime ideals. That's pretty simple. And there's nothing topological about that definition. The set of all the prime ideals of R. Now, let me point some things out. The prime ideals, you probably think of a prime ideal, my gosh, prime ideals are huge. Uncountably infinite things in this, maybe it's in a polynomial ring. We're not restricting the ring whatsoever right now. But prime ideals have lots of stuff in them usually. But the prime ideals are going to be points in this space, the spectrum of R. They're going to be the elements. They're going to be the points. And if you think about that ring, or any polynomial ring in some number of indeterminates over, we'll keep it C for the sake of simplicity, then these prime ideals are going to be generated by irreducible polynomials. Irreducible polynomials. What about those irreducible polynomials has anything to do with geometry? Well, it's the zeros of those irreducible polynomials that's going to be of interest. So since the polynomials are irreducible, then the ideals are prime ideals. And so studying the topology of the prime ideals is going to give us information about the topology of the zeros of polynomials. And that's the geometrical connection. And it's huge. We won't even begin. You have to take a class in algebraic geometry in order to get all of that. But you're getting, in this class, you're getting some of the jargon. Krull dimension is part of the jargon. The radical of an ideal is part of the jargon. And certainly the spectrum of the ring is part of the jargon. The spectrum of a ring is a set of all the prime ideals. So what's the spectrum of the integers? Well, it's a set of all the PZs, where P's are prime numbers, and so union the zero ideal. Those are all the prime ideals in Z. So that collection, that infinite collection of prime ideals, make up the spectrum of Z. Okay? And there's any number, of course, of topologies that you can put on a set, especially one that could be really pretty big. But there's a particular topology that has been shown useful in connecting the algebra with the topology with the geometry, and that topology is called the Zariski topology. So we're going to place a topology on spec R. Keep in mind, you can put any number of topologies on spec R, but this is the one that has been useful. And by the way, you'll probably find some research papers that say, oh, there are other topologies on spec R that are more useful than the Zariski topology. But we're going to learn about this one because this is the one that historically has given people the most mileage. So, define V of I for I, any ideal of R. To be the set of all prime ideals that contain I. So, want to get used to the notation. V of I is equal to the set of all P in spec R. I should use a capital S here since I want to be uniform about it. Such that P contains I. Okay, you can do that for any. You can do that for any ideal. For example, and by the way, the V, that just might bring to mind the word variety. Doesn't mean there's lots of kinds of it. I'm talking about an algebraic variety, the set of solutions of polynomials. Okay. Now, what, for example, is V of 0? 0 is an ideal. What is the set of all the prime ideals in spec R that contain the 0 ideal? Well, by definition, all ideals in any ring contain the 0 ideal, so certainly all the prime ideals do. This is going to be the whole space, spec R. And by the way, the ring itself is always an ideal of itself. What's going to be V of R? Well, V of R is a set of all, break everything down to the definition. It's a set of all the prime ideals in spec R that contain R. What prime ideal could possibly contain the whole ring? There are no prime ideals that contain the whole ring. This is the empty set. Now, isn't that nice that we get the whole thing and we get the empty set? Sounds like the basis for a topology for me, to me. So here's our topology, and we'll call it tau as usual. Tau is going to equal the set of all subsets of spec R such that U equals the complement of V of I for some ideal of R. That is to say, the V of I are the closed sets. I'm going to say the closed sets to be, because we haven't done anything with openness or closedness yet. I don't know if it satisfies the properties of being a topology. So do these satisfy the properties of being closed sets? We'll have to find out. But these are the candidates, okay? These are the candidates for the open sets, the complements of these guys. So we did this back in topology in the first semester. Sometimes you define a topology through the back door by defining the closed sets first and then taking their complements. That's what we're doing. Ooh, time for a fix. Okay. By the way, I'm sure you guessed, tau is called the Zariski topology. For spec R. Now, because of the relationship between prime ideals of a polynomial ring and the solutions to the polynomials that generate that ideal, many people talk about the Zariski topology just geometrically, rather than worrying about the prime ideals. You can do that. The two have a relationship together, and so there's no difference in the basic topologies, except they're canonically equivalent. So, theorem 33. Tau is a topology. Now, you already know there are three things to show. O1. We have to show that the whole space and the empty set are open. Well, since the empty set is equal to V of something, then spec R, which is the complement of the empty set, is in tau. And similarly, since spec R is equal to V of the zero ideal, I don't need two commas, then phi, which is the complement of spec R, is in tau. So that gives us our first one. Okay? The second thing that I need to show is that if I have any number of elements of tau big, small, two of them, uncountably, infinitely many of them. If I have any number of elements in tau, then the union of those two has to be an element of tau. So let's do that. For every alpha in, what did I use, gamma? Yeah, gamma, where gamma is some index set, let U sub alpha be in tau. Okay, we don't know they're open sets yet because we don't know this thing is a topology. We can call those open sets as soon as we know it's a topology. But right now they're just in this collection of complements. So let U sub alpha be in tau. How do I get the union of all of those BCs in to be in tau? Well, first of all, notice that there exists I sub alpha ideals of R such that U sub alpha is the complement of V of the I sub alphas. That's exactly the definition. For each one of the U sub alphas, there's some ideal that the complement of V of that ideal is the given U sub alpha. So that's just the definition of U sub alpha being in tau. Okay. Now, how are we going to get this to come out? Well, let's do the arithmetic. The union over alpha and gamma of U sub alpha is equal to the union over alpha and gamma, copy, right? The complements of the V sub alphas, which by De Morgan's law is the complement of the complement of the intersection of the V sub alphas and we claim, let's do it this way. I was just going to state it, but we're going to prove it. And we claim that the intersection of the V sub alphas. Now, what has to be true? In order for this to be in tau, I need the complement of this to be in tau, which means I need this without complement to be one of the V's. So I need to find some ideal so that the intersection of all of these is V of that ideal, because that's the only way that it's going to be a candidate for being closed. So I need to find something. Now notice, the more and more of these things that you intersect, the more you're limiting this set. And so the ideals would have to get bigger and bigger. Let me show you what I mean. We claim that the intersection of these is actually V of the sum of the I sub alphas. We do have to prove that, but first I have to define it. What does the sum of I sub alpha for alpha and gamma mean? And this is normal in algebra, that what I mean by this sum, now there could be uncountably many of these little monsters. How do you get an uncountable sum? And the answer is, it's the sum of all of these is the collection of all of the finite sums of these taken a finite number at a time. okay? So the sum over alpha and gamma of I sub alpha is equal to the set of all finite sums. So we'll say from I equals 1 to n of a sub, let's see, how do I want to do this? Yeah, a sub alpha 1 plus a sub alpha 2. I don't need to do that. It's the finite sums of a sub alpha I such that a sub alpha I is in I sub alpha. And let's see, I'm not stating this very well. Yeah, I am stating this very well, actually. The whole point being that I'm taking finitely many of these at a time. Now, there may be some huge number of them. I'm not going to leave any of them out, but only finite sums make up this ideal. Is this an ideal? Now, the temptation would be, rather than to take the sum of these ideals, to just take the union of them. But the union of ideals is not necessarily an ideal. Consider the integers, for example. What's the union of 2z and 3z? Well, the union of those two things is all of the integers that are either multiples of 2 or multiples of 3, but that's not an ideal, because not every, well, you know what I mean. So unions of ideals are not necessarily ideals. Sums of ideals are. So it is easy to show, and this is left as an exercise, that the sum of I sub alpha is indeed an ideal of R. Okay? Not a tough problem. But still, my statement here needs to be proven. We claim that this intersection is equal to the V of the entire sum. We have to prove that. So let's go this way. Suppose that P is in the intersection for alpha and gamma of V of I sub alpha. Okay. I want to show that P is actually in here, so suppose it's not. If P is not an element of V of the sum, then there exists some I sub alpha sub I, where I equals 1 to n, such that the sum from I equals 1 to n of A sub alpha sub I is not in P. If P is not contained in the set of all things that contain that ideal, then P doesn't contain this ideal. So there must be something in the ideal that P doesn't contain, so that doesn't live inside P. But what's the problem with that? Well, P is in the intersection of all of those. So P contains every one of the I sub alphas. So that's a contradiction. Okay, let's go the other way. This was obvious. If P is in the sum, in V of the sum of the I sub alphas, clearly P contains that sum implies that P contains each I sub alpha. So P is in the intersection of all of those. Okay, so that part was easy. O3. Now what's O3? I have to show that if I have any two, and by induction it would be any finite number, but if I have any two of these open sets, they're not open yet, but any two of the U's, U1 and U2, I have to show that the intersection of those two is another element of tau. So suppose that U1 and U2 are in tau. Okay, well, break everything down to the definition. That means that U1 is equal to the complement of V of some I1. U2 is equal to the complement of V of some I2, where both of the I sub j's are ideals of R. Okay. Then, now, what do I need to show? I need to show that the intersection of these two is in tau. What does that mean? That means everything that's in tau is the complement of V of something. So I have to show that the intersection of these two is the complement of V of some ideal. I got to cook up that ideal. That ain't going to be too hard. So we must show that U1 intersect U2 lives in tau. Okay, well let's do the arithmetic here. The complement of U1 intersect U2 is what I'm really interested in here. And what is that equal to? By De Morgan's law again, it's the complement of U1 union the complement of U2, which by definition, the complement of U1 is V of I2. I mean, V of I1. And that the union of that with V of I2. Okay. We must show that this is V of something. That this union is V of something. Well, what might it be V of? If I'm gluing these two things together, then I need to shrink the ideal. So one way to shrink it would be to take the product of the two ideals. Now, I could have tried the intersection of the two ideals, but it turns out that having done the arithmetic on this so many times, and I've done it a few times, what works is the product, and you're going to see why. We haven't used yet the primeness of any of these ideals, the fact that any of them are prime. We have to use that. So we're going to use it. It's coming up. It's all part of O3. But first, let's erase O1. And O2, goodbye. Most of O2. I hope that the pace at which we're doing this is good. Because the material is a little bizarre, I recognize that. I'm trying to do this very slowly. So, maybe get back with me and let me know if the pace has been suitable for you guys. I don't want to just blaze through this. One of the nastiest experiences of my life, literally, was when I was in college and I was taking a class in differential geometry. And my instructor must have taken speech lessons from an auctioneer. The differentiable manifold is you got this, and you're going to take the tangent bundle, and if you intersect that, take the partial derivatives, and I was going nuts. Barely survived. And so I don't want that to be your experience here. I want you to come through here and say, you know what? I get this stuff. I understand it. And maybe you'll actually remember a couple of the things from it. That would be cool. Maybe you'll entertain your children on a trip someday by showing them something about the Zariski topology. You might not want to do that when they're 6. They could have a little trouble with it. But I have to show that this union is V of something, and I1 times I2 turns out to be the something. So how do you show two sets are equal? Show each as a subset of the other. So suppose that P lives in V of I1 union V of I2. Then either P is in here or P is in there. Well, what's this? This is a set of all the prime ideals that contain I1. So either P contains I1 or P contains I2. Okay? Hence, if P contains I1, what about I1 times I2? Well, notice something. Since these are ideals, they suck in multiplication from anything in the ring. Certainly suck in multiplication from each other. So I1 times I2 lives inside I1. It lives inside I2. It lives inside the intersection. Might be smaller, but it lives inside the intersection. So if P contains I1, then P contains I1, I2, because this lives inside I1. If P contains I2, then P contains I1, I2. So because I1 and I2 are ideals, I1, I2 is an ideal and P contains it. Therefore, P lives inside that variety. Now let's go the other way. Let P be an element of V of I1, I2. Well, break everything down to the definition. What does that mean? That means that P contains I1, I2. So when I multiply this ideal times this ideal, that lives inside this prime ideal. But P is a prime ideal. So if the product of two ideals live inside here, one or the other has to live inside here. So since P is prime, since P is a prime ideal, that's the definition of a prime ideal, that P contains I1 or P contains I2, so P lives in V of I1 or V of I2. And that, as they say, is that. So tau is a topology. The Zariski topology passes the test. Okay. Now, let's compute. Let's compute the Zariski topology on a set or two. Let's say, here's an example. What is the Zariski topology for spec Z? What is it? What are its properties? Well, let's enumerate spec Z. We already talked about it. Let's write it down. Spec Z is equal to the zero ideal and all of the PZs for P prime integers. So an infinite set, that's the set of all the prime ideals for spec Z. Now, for I some ideal in Z, what is V of I? Well, I'll let you stew on that while I erase the other board. Stew. Okay. Now, you probably learned in abstract algebra. If you haven't yet, you will. Every ideal of the integers is a set of multiples of some single integer. Okay, you don't get ideals of the integer that require more than one integer to generate them. I've already told you what the term is. Z is a principal ideal domain. Every ideal of Z is principal. It's a set of multiples of a single integer. Well, we're going to use that. So whatever I is principal, since Z is, and this is called a principal ideal domain, a PID. Many things that you learn when you study commutative algebra in abstract algebra, you learn that every principal ideal domain is a unique factorization domain. You learn lots of things about those. But right now, Z is, every ideal of Z is generated by only one integer. So, say that I is equal to the ideal generated by n. Okay. Now, what's something that you learned about n? N might be a prime, n might be a composite number, but one thing we know for sure, every PID is a UFD. It's a unique factorization domain. There is a unique factorization of n up to either plus or minus 1, but a unique factorization as a product of primes. Now that includes multiplicity. So, if you have n is equal to 12, then that's 2 times 3. And so, but that factorization is unique. Well, I don't even care that it's unique right now. Therefore, n is equal to P1, P2, out to P sub k, where the P sub I are primes. Okay? Therefore, n is in P1Z, P2Z, it's in all of those, it's in P sub k Z, n is in all of those. Okay? Hence, I is a subset of V of the P sub k for all k. These things are all elements of spec R. And so what have I figured out? So I is contained let's see, did I say that right? Okay, I is contained in all the prime ideals P sub I Z. Therefore, I is contained in only finitely many of the elements of spec R, spec Z in this case. Only these elements contain I. So only finitely many of our infinite number of prime ideals in Z. So what does this look like now? The only closed sets are finite. Almost. The only closed sets are finite, except for all of spec Z. That's obviously not finite. There are lots of prime ideals in there. So the closed sets are finite or all of spec Z. This is the cofinite topology with one small exception. What's the exception? V of 0, which is equal to spec Z, so this finite set, the zero ideal, is not closed. In fact, what is its closure? It's very, very not closed. The closure of this little guy is the smallest closed set that contains 0. You know what that is? Well, I'll let you think about it. But the Zariski topology on spec Z is essentially the cofinite topology, but it does have the exception that this prime ideal, even though it's finite, is not closed. Okay? Now, just some reminders of some things that we've already talked about. We talked about the radical of an ideal. We've talked about, we proved Kroll's theorem, the fact that the radical of an ideal is the intersection of all of the prime ideals that contain the ideal itself. Okay, we proved that. It wasn't too hard to prove. We defined the Kroll dimension as being the supremum of all of the lengths of chains of prime ideals. So if I've got this ideal, it's contained in that one where the contain is proper containment, so not equal to. And this one is properly contained in this one, properly can blah, blah, blah. And however far that goes, that's the dimension. Now, do you think it's possible that it might go on forever? The answer is yes, it is possible. And so we're going to talk about rings where you have a limitation there. And what else did I want to talk about in this regard? Well, some examples. Suppose that you have a field, okay? If you have a field, what is the dimension, the Kroll dimension of the field? Well, how big a chain of prime ideals can you have in a field? There's only one. The 0 ideal is the only prime ideal. It is therefore a maximal ideal. Fields don't have any ideals except for 0 and the whole thing. Such a ring is called simple, and a simple ring with 1, a simple commutative ring with 1, is called a field. Okay, so, and that's easy to prove. I think we proved it last semester in Linear 2, actually. But, so the Kroll dimension of every field is 0. What about, suppose that you have a ring like the integers, where every non-zero prime ideal is maximal. So rather than to just talk, let me write. I really like these boards. Praise God for a good friend of mine who helped me put this one up. That one I already had. But what is the dimension of the set of integers? Well, it's the number of primes in the largest chain of prime ideals. And of course, 0 is a prime ideal. That's as low as you can go. And then any prime ideal above that, p times z. But are there any prime ideals that contain pz? No, pz is a maximal ideal. So the Kroll dimension is 1. That's the longest chain. And so only one extension. So the Kroll dimension, as a matter of fact, if you have any PID, any principal ideal domain, Kroll dimension of that is also 1. And I've already told you that the dimension, if I have a field, and I attach n indeterminates, take the polynomial ring over that field, the dimension of this thing is n, where k is a field. Let's see, what else? Let's do another definition. Suppose a ring, suppose a topological space. Let's do it this way. Suppose a topological space has ascending, I haven't defined this yet, ascending chain condition, henceforth forevermore ACC. If you studied a little ring theory, then you may have seen ACC before, but has ascending chain condition on open sets. Now, what does that mean? i.e., U1 subset, and this can just be subset, U2 subset, U3 subset, blah, 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 subset. If this chain must eventually become constant, it must eventually stop. So there exists some u sub m, say, so that u sub m contained in u sub m plus 1, contained in, so that all of these are equal. No use writing it in 2 statements, I can just do it in 1. So from some point on, if they're all equal, it doesn't continue getting bigger, then that's called the ascending chain condition. So, but ascending chain condition is not what I'm defining. I did want to define that. Then we say the topological space is Noetherian. This is an interesting thing. Noetherian comes from a very well-known mathematician. I believe her name was Emma Noether. And her work on ascending chain conditions, part of that was in rings. In rings, if you have the ascending chain condition on, say, left ideals. So you have a left ideal, it's containing another left ideal, containing another left ideal, and if eventually every such chain has to stop, that ring is called a left Noetherian ring, or you could have a right Noetherian ring, or you could just do ideals and have a Noetherian ring. There's also a descending chain condition. And we're not going to be so concerned with that here. Context is just a little different. But in ring theory, if you have the descending chain condition, the ring is said to be Artinian, named after a mathematician that you probably remember well, Emil Artin. Artinian rings are greatly involved with an understanding of the structure of rings. For example, if you have an Artinian ring that is semi-simple, meaning that one of its radicals, called the Jacobson radical, is zero, is trivial. And so we're not going to talk much about the Jacobson radical, but the Jacobson radical is the intersection of the annihilators of all the faithful irreducible modules, whatever the heck that means. Look it up. It's a fascinating thing. But here's the beauty of it. If the Jacobson radical of a ring is zero, and the ring has a descending chain condition on ideals, then that ring can actually be embedded in the direct sum of matrices over division rings. Now that's a huge result. It's called the Artin-Wedderburn theorem, but it really glues down the structure of certain rings, non-commutative rings, that you get matrices over division rings all glued together. Fascinating field. So if you get a chance to study non-commutative rings in grad school, I highly recommend it. It's a beautiful theory. So let's press on. Noetherian topological spaces. The way that I chose to remember which was which, Noetherian was ascending chain condition and Artinian was descending chain condition, is that I remembered that the letter A was associated with one of them, the Artinian, and so it couldn't have been Artinian was descending chain because that would associate the A with the D. So whatever floats your boat, that worked for me when I was taking Math 613 at USC. Okay. Next. Let's see. Theorem. Now that we know that we have this topological space on the prime spectrum of a ring, the collection of all the prime ideals, what are the properties of that topological space? Separability, compactness, connectedness, and all that kind of thing. And you can do all of that stuff up, but we're going to do a little bit of it, namely, spec of R is the first degree of separability, T0. Because we're at the end of class, I'm going to save the proof. The proof is easy. So I'm going to save the proof for next time. Then we're going to do some discussing about the prime spectrum. But I'm having a good time. I hope you are. And God bless you guys. We'll be talking to you again soon. Goodbye.